So last time we talked about photolithography, the light source and the mask and the system. So now we look at the resolution of the photolithography. So to study the resolution, so we need to know about the light diffraction. Here the light diffraction, so we have the plane wave, and this is aperture. So you can consider this one as a mask. This is like a photo mask. On the photo mask, we have a small opening here. We have a small opening on the photo mask. So this part is chrome, and we have glass on the glass. So you can see the light right after the mask opening is the light intensity is something like this. So this is the ideal case. But after some distance, you can see the light, the profile become this irregular profile. So this one is the near field. Very, very far away, so we have the far field. Far field is called the Fraunhofer diffraction. So near field is called the Fresnel diffraction. For the far field, we have the light intensity something like this. I will put a lens. I will put the objective lens. Then this light intensity will form image. On the image plane. F. So now we look at the near field first. Near field Fresnel diffraction. So this corresponds to the case of the contact or proximity exposure. Let me see contact proximity. If you remember here, so this one is contact, this one is proximity. So we have a gap. Between the photo mask and the photoresist. So this is the near field. So we have this is the photo mask. So this one you can consider this one as the chrome photo mask, and this is the opening with the width W width, and then we have a gap. This is the gap here. And here is the resist, and this is the wafer. So the light intensity profile in the resist is something like this. So we can see that so the edge of the image rise gradually from there. You can see the light intensity rise gradually from 0 to the certain value. So the intensity oscillate. Light intensity oscillate. You can see the oscillation here, and oscillation decays as one approaches the center of the image. You can see it's more flat here, less oscillation. So the oscillation is because of the constructive and destructive interference of the Huygens wavelength. So if you want to know, you can check Huygens principle from the internet, and we will talk more about the Huygens principle next term in the NE343. So basically the Huygens wavelength, you can see for this opening we have many we say a delta x, a dx. So we have many, for this small opening, we divide into many small parts, that's a dx. Which part we can assume we have a small light, this like which part we have a small a wavelength. And those wavelengths, they will, for this spot, all the wavelengths will come here. And they will interfere constructively or destructively interfere. Then you form this one tall and low images. So when aperture is small, the actual oscillation are large. When aperture width is large, the oscillation rapidly die out, and one approach the Ray optics for the big apertures. So this gives you because of this slope here, this limits the resolution. So it's given by W is given by lambda G, roughly. This makes sense, I think. You see, smaller lambda gives you smaller resolving power, smaller feature size, higher resolution. Smaller gap also gives you higher resolution. That means smaller minimum feature size that can be resolved. So here, this is the roughly, but here you have the G plus T over 2. That means the gap is counted from here to the middle. The resist thickness, this one is T. The gap plus half T means gap is considered from here to the middle of the resist. And there is also a factor 0 over 2 in the front. So this formula is very difficult to derive. So you just need to know about it. It's okay. So roughly lambda G is the resolution for the proximity exposure. So now we look at the far field of Fraunhofer diffraction for the projection exposure. For the projection exposure, so this is the projection exposure. So we have the photo mask, and we have a lens, objective lens, and we have image on the resist. So we have a lens to collect the light, and the same thing here. So we have a lens. This is the lens. So the light will be collected to form the image at the focal plane. To form image here at the focal plane. So this is the projection lithography. But actually, another focal plane is a little bit distance away from the focal plane. So you can see this one is the proximity as we have seen in the previous slide. This one is the far field. This is the far field. This corresponds to the case of the projection exposure. So you can see this is the light intensity for the far field. You see we have the maximum, here, and if we look at the dashed line, we have another maximum here, another maximum here. We have many maximum and minimum. So here, the I should be normally we say it as E. So this is the amplitude. Amplitude E. So this one can be the solid line can be higher than 0 or smaller than 0. So the intensity is proportional to E square. This is the intensity proportional to the amplitude square. So the intensity is the dashed line. You can see it always positive. And we have one major peak and we have smaller peak here. So those smaller peak is the order. We call it diffraction order. So this is the zero order. The zero order here corresponds to this peak. The zero order here, the first order here. This one is first order corresponds to this small peak. Then we have second order. So this is the second order. So we have many diffracted light. So those peak is the diffraction order. So how much light is collected? This determines on the size of the lens. So obviously, the larger the lens, more diffracted light will be collected. So the capability for the lens to collect the light is the numerical aperture. So numerical aperture is defined. Numerical aperture is the optical system, is a measure of the ability of the lens to collect the light. It's defined as n sin alpha. So n is the index of the medium. Here if it is higher than n equal to 1. Otherwise n is not equal to 1. Sin alpha. So alpha is this angle here. This is alpha. So you can see the larger the alpha angle, the bigger the lens, right? So the numerical aperture is the capability of the lens to collect the light. The larger numerical aperture, the bigger the lens, and the more light will be collected. So this is also an important concept for the optical microscope. Now here's the numerical aperture. I will look at here. I will buy an optical microscope. You can see more here. Yeah, you can see. I will buy the objective lens for the optical microscope. You see, have the number here. This one is 4. Numerical aperture 0.1. Numerical aperture 0.25, 0.65, and 1.25. But here you see the word oil. When you have in oil, you have numerical aperture higher than 1 because the index n is higher than 1. So here the same thing. So 0.1, when you have 100 times, you can have the numerical aperture to be 1.25. But this is because of the you use immersion oil. So we have the oil. The index for the oil is 1.5. Then you can get numerical aperture to be 1.25. This is the idea of the numerical aperture. So you can see again. This is we have the opening, we have the lens. Smaller lens, you get image like this. You have the maximum, minimum. The bigger the lens, we have very big lens. You get a spot. But this is not in the same scale. This one actually should be much smaller. This spot than the spot here. So this is the idea of we have bigger lens. It's better focused. So the light intensity here, the spot like this, is given by something called area disk. For example, if you have a lens, this is the sunlight very far away. You have the perfectly plane wave, then it will be focused to the focal point. If you look at the focal point, it is not a point. It is actually, if you look at here, it's not a point. It is actually something like this. So how the feature set here, the feature set here depend on the size of the lens, how big is the lens, and also depend on the wavelength. So you can see this is the intensity profile of this area disk. This is the light intensity at this focal point. The same thing is here. Here has the parallel light, so the light intensity here is given by something like this. So the radius here is given by 1.22 lambda f over d. Lambda is the wavelength, f is the focal length, d is the size of the lens. You can see we get a perfect point image. Only if lambda is 0 or f equals 0 or the d equals infinity. You have infinite. If the lens is infinitely large, you get point image. This is the ideal case. It's point image like something like this, like a delta function. Point image. Only infinity at x equal to 0. So now we look at the resolution. Resolution means how far away two spots can be resolved. Here have two spots as the object. Here the two spots as the image A prime and B prime. So how far away they can still be resolved. This one is given by a Rayleigh criteria. Here are the two images. This one you can consider this one as this one maybe you can say is A prime. This one is A prime, and this one is B prime. You can see in this case the two images are well resolved. There are two. Each of them is some A or B. Each of them is something like this. This is well resolved. When they are too close, it's unresolved. So how far away we can still say that it is well resolved. So this is given by the Rayleigh criteria. So Rayleigh suggested that a reasonable criterion for resolution is that the central maximum of each point source lies at the first minimum of the array pattern. That means the maximum to this part. So this is the maximum of the B prime. If this is B prime. So maximum of the B prime overlap with the minimum of the A prime. Then we say A and B, A prime and B prime, they are well resolved. So in this case, we do not care about how far away it is A and B. We do not care about the distance here. We care about the distance here because we want to know how small, how close we can put on the resist on the wafer. This is the wafer. So we care about how close they can be put on the wafer and they can still be resolved. We don't care about A or B. So this is the Rayleigh criteria. Other criteria is kind of arbitrary. You can see something different. We say less than or more than that. But this is a roughly estimation of whether two spots can be resolved or not. So this Rayleigh. So now we look at this Lord Rayleigh. So he had other discoveries. Yeah, there's the Rayleigh. So he won the Nobel Prize. He won the Nobel Prize in 1994. In 1994, he won the Nobel Prize because he discovered the argon. Discovery and isolation of argon. So because of this, he won the Nobel Prize. But actually, another thing, a big thing from him is the Rayleigh scattering. Where is it? Rayleigh scattering. So we know that the color, the sky is blue. The sky is blue. So why the sky is blue? So this is because of the Rayleigh scattering. So Rayleigh scattering said that. So the Rayleigh scattering said that. So the longer the wavelength, the the smaller the scattering is something. Well, let me see whether I can write here or not. I cannot. So you see, so the scattering is universally proportional to the first power over the wave loss. Universally proportional the first power over the wave loss. That means the scattering is proportional to 1 over lambda power 4. So the blue light has short wave loss, so it's more scattered than the red light that has long wave loss. That's why when you look at the sky, when you look at the sky, the observer sees only scattered light. So the blue light is more scattered. That's why you see the sky is blue during the daytime. But if you look at the sun, directly at the evening or in the morning, you see the sun is red. You see the sun is red in the evening or in the morning, because the blue color light is scattered away, and you see more red color light that is less scattered. That's why the sun appear red in the morning or at night when you look at the sun directly. So this is the Lord relay. So here we have the relay scattering, and here the relay criteria for the resolution. So you can see that this, we know the distance from here to here. From here to here is given by 1.22 here, from here to here, 1.22 lambda f over d. You see, so resolution given by 1.22 lambda f over d. So resolution here means how far away the two spots can still be distinguished on the wafer or on the photoresist. This is the resolution we can get for the lithography. 1.22 lambda over d. The lambda, when you have the medium, then it becomes lambda over n. This is the wave loss when you have the medium d. So d is the size of the length. So d equal to 2 times f tangent alpha, right? So this is the f. This is f tangent alpha. So roughly equal 2 times f sine alpha. So when this angle is small, tangent alpha is the same as sine alpha, so 2f sine alpha. So you can see here, 2f sine alpha, you cut out the f, you have 0.61 lambda over n sine alpha. N sine alpha by definition is the numerical aperture. So usually we say 0.61, we say K1, we say the K1 value. The K1 factor has no well-defined physical meaning. That means everything else, besides wave loss or the numerical aperture effect, everything else, like how the lithography equipment is designed, everything else is put in the property of K1. So to have the higher resolution, that means smaller r, we can have smaller, shorter wavelengths. We can increase the numerical aperture to be higher than 1. We can decrease the K1 factor. So we have many things to decrease the K1 factor, and also we can reduce the wavelength. So nowadays we use 193 nanometer wavelength plus 13.5 nanometer. 13.5. This is the extreme UV lithography. So today, so both immersion with 193 nanometer and dry 13.5 nanometer extreme UV light lithography is used for the manufacturing of the most advanced IC circuit. So now let's look at the example. This one, 248 nanometer blurred. This one, higher numerical aperture. This one, it gets better image. This shorter wavelength gives you better image. Higher numerical aperture than this one, you get better image. This is even higher numerical aperture. This is even higher numerical aperture, get better and better image. This one, 157 nanometer. This one, you get better image. This is the immersion. Immersion means we have oil, but actually it is water. It is water, not oil. It's the same thing. So we have the numerical aperture higher than 1 when we have the immersion in the water. You get better image. This one is the extreme UV light. You get much better resolution because the wavelength is so short. Now here there is the word annular. Annular is the off-axis illumination. So we will talk about we will talk about off-axis illumination in the NE343 next term. So this is one trick to decrease the K1 value. So this one, 157 nanometer. 157 nanometer has been under research for many, many years. But around year 2000, this one is give up. This one immersion argon 183 nanometer immersion win off. So this one win, this one lose. As a result, the company. This is ASML, ASML. This is the top lithography company, ASML in Denmark, not in Denmark, in the Netherlands. This one, because they use the immersion, they won over this 157 nanometer. So because of the choice, so ASML choose this one, and Japanese companies like Nikon, they choose 157 nanometer route. As a result, this one, the Nikon, the Japanese company, maybe CON, the Japanese company, the lithography, Nikon or Canon, those companies, they lose to ASML because of they take the wrong way. They put too much effort in the 157 nanometer, not enough effort in immersion lithography. So besides resolution, we also care about the depth of focus, because the wafer. So if the wafer is, if the wafer is not flat, that's maybe this area is well focused, this area not well focused. So this is the problem. So we need to care about the depth of focus. For the photography, we have the same idea of the depth of focus. This one is well focused from front to the back. This one, only this flower is well focused, the background is blurred. This one we use a big lens. This one we use a small lens, small aperture or small lens. So normally the camera in a cell phone, they are too small, so you can only take this kind of image. It's very difficult to take this kind of image. And this is the idea of the depth of focus. So this one is also given by a Rayleigh, the same Rayleigh. This is the Rayleigh criteria for depth of focus. So he said that the length of two optical paths, one on axis, one from lens edge or limiting aperture, not differ by more than lambda over 4. So what does this mean? For example, the point B, at the point B, focal point, the two branches have equal paths. So one branch from here to O to B, and the other branch from here to A and to B. So they have equal optical paths. So this is the idea of the focus. This is the idea of optical imaging. They have equal optical paths. So this is the focal point. At point C, this is no longer focused. The difference between the two paths is given by lambda over 4. Let's look at. So we know that at point B, the two branches have equal paths. So on axis, for the on axis one, for this branch, the optical path increased by OC minus OB. So from increased by OC minus OB, so equal to this part. So on axis, from here to here, the difference is given by delta. For the from edge come from here to A, then to C. So the difference from A to C minus A to B, the AC minus AB. If we draw a line like this, it's given by DC. DC is given by delta cosine theta. So this is theta. This one is also roughly theta, because the delta is much smaller than the focal length. So then you have delta minus delta cosine theta, delta minus delta cosine theta equal to lambda over 4. So this is the Rayleigh criteria. And then we can say this is the cosine theta. So we know about this approximation. So cosine is equal to 1 over 2 theta square. So you can 1 minus theta square over 2. Then it's given by this formula here. Then from here, we have theta square. So theta for the small angle, theta roughly equal to sine theta, equal to d over 2 lambda. So d over lambda divided by 2. So this is the theta. This is actually tangent theta, but the same thing, very close to sine theta. This is given by numerical aperture. You can see sin theta is numerical aperture for the case of the n equal to 1. N equal to 1, the sin theta equal to NA. Then you can find out the depth of focus delta is given by lambda over 2. So delta from here, this one, you can see delta equals lambda over 2 theta squared, so equal to lambda over NA, theta is NA, so 1 over 2 is replaced by this K2 value. It is given by this formula here. This is the depth of focus. So you have the plus, you have the minus, because you have the, this one is, you can draw, so the, it can be defocused this way, it can also be defocused the other way. That's why you have the plus and the minus. So this is the depth of focus. So now let's look at a better way to describe the image contrast, to describe the image of contrast. So here we assume we have a mask. This mask is the line array. It is a line array structure like this. Block, open, block, open, block, open. So this is the mask. Then after the length is found image on the resist, something like this. This one is 4 times smaller. So the feature set here is 4 times smaller than the feature set on the mask because we have the 4 times reduction. So ideally, the light intensity should be something like this. But because of the diffraction, the light intensity on the wafer become something like this. So same thing here. This is the mask, this is the length, the light intensity is something like this. If you draw it, it's like this. So the MTF is called the modulation transfer function, is defined as Imax. This is the Imax. This is I minimum minus I minimum divided by Imax plus I minimum. This way give you some more accurate description of the image contrast. Because what we see previously, the relay criteria is too rough. We need a better way to tell about the resolution. So this, by defining the modulation transfer function, later on we can figure out what is the resolution, which is more accurate way than the relay criteria resolution. So here is the so actually there is also the modulation transfer function for the photography. You can see here because lithography is kind of similar to the photography. So A is the original test pattern. This is the test pattern, and this is the intensity. C is the line profile of the test pattern. It's perfect. So B is the image after the photography. So B is the photography image. You can see it got blurred, and this is the light intensity. So here it's okay. We can still have the maximum, minimum like 1, minimum like 0. But when you get closer and closer, you can see the contrast becomes smaller and smaller. But this is the idea of the modulation transfer function. So obviously, the closer they are, the smaller the pitch. That means higher spatial so this one has higher spatial frequency, the worse the modulation transfer function. So the modulation transfer function also depends on the spatial coherence. So the concept for what is spatial coherence, you can see ideally we have a point source. Then when the light come out, it is coherent. This is the coherent light. Coherent light have the phase to space relationship. The relationship is given by, if we talk about the electrical field component of the electromagnetic wave, then this one is given by the amplitude E I K minus omega t. You can see, so this part is the phase. The R here is the space. So we have well-defined phase and space relationship. But for the non-ideal case, this one we have the light source that is this big. The light source is this big. then the light incidence on the mask is something like this. This one is called incoherent light or partial coherent light. This one is the partially coherent light. The wavefront that are only partially correlated is not well defined like this. The wavefront on the mask is only partially coherent or partially correlated. So the S is the spatial coherent S is defined as the source diameter S divided by the aperture diameter, which is D. So this is the spatial coherence. So it is an indication of the angular range of the light wave incident on the mask. You can see here we have everything is normal to the mask. For this case, so we have the light that has the inclined incidence on the mask. The small s is not always good. So ideally, this one s equal to 0, but actually s equal to 0 is not always good. Sometimes we want s to be a little bit some size. So this we have the light incident from the tilt, from inclined direction. So this idea similar to the off-axis illumination. So the off-axis illumination will give you better resolution than this normal illumination. So we will talk about off-axis illumination next term in the 353. So now we look at the effect of the spatial coherence, on the modulation transfer function. So it's given by this graph. So the S here is the spatial coherence. This one is the modulation transfer function. So in this case, so we have the grating photomask, and the light intensity profile on the wafer is given by 2W. The light on the wafer is 2W. The grating period on the mask is HW because we have photon reduction. So on the wafer is 2W. So the horizontal axis is called normalized spatial frequency. So spatial frequency is defined by 1 over 2W. So 1 over 2W. This is the spatial frequency. So 2W. You see, 2W is the pitch. Is the period. How is it? 2W is the pitch or period of the grating. So 1 over 2W is the spatial frequency. Divided is, but this one is normalized. So normalized to what? So normalized to the Rayleigh criteria cutoff frequency mu 0 1 over r. Normalized to the Rayleigh criteria cutoff frequency, which given by this one, right? NA0 given by this one. So this is axis 1 over 2W normalized to 1 over 0.61 lambda over NA. This is the Rayleigh criteria. So this is the x-axis. So y-axis is the modulation transfer function. So now let's look at whether this makes sense or not. So you can see, so the higher frequency, the smaller modulation transfer function. So higher frequency means smaller W, we get smaller modulation transfer function. So this makes sense because you can see smaller the pitch, smaller the W, you get smaller the modulation transfer function. So this makes sense. Another thing you can see that so this one is s equal to 0.5, this one s equal to 1, this one 0.25. So you can see for the larger s, it's good for the smaller features. Smaller features means higher frequency. You can see this s equal to 1. S equal to 1. It's very big. S equal to 1 is very big. But this case is better than s equal to 0.25. It's also better than s equal to 0.5. So larger s is good for the smaller features, but bad for the larger features. So larger features is here. You can see, so s equal to 1, if you look at here, this one is not as good as this one, and this is not as good as this one. So that means that, so we want some trade-off. We need some trade-off. We need some trade-off for the spatial coherence s. So normally for the commercial product, the s is chosen as 0.5 to 0.7. This way we get good resolution for the small features, and also we get some good resolution for the larger features. So we will have some assignment on the modulation transfer function and also from this curve. I hope you can understand this curve. Basically, this curve tells you if you know the feature size and you know the numerical aperture, or you know the wave loss, you know spatial coherence, you can get the MTF. You get the MTF, and if you know the MTF, you can also figure out what smallest W you can get. So later on, we will have the definition of CMTF. There is a critical MTF. This is the property of the resist. So eventually, as you can imagine, so the resolution usually depends on the photoresist. So we have very good photoresist, low MTF can be resolved. We have very poor photoresist. You need a very good MTF in order to resolve it. This is a periodic structure. A periodic structure is something, this is the MTF, so something like this. If we look at the Rayleigh criteria, this one, you can imagine, this one is the I max, this one is the I minimum, I max, I minimum. This, you can also get the kind of MTF from this minimum and maximum light intensity. So Rayleigh said that in this situation, overlap the minimum with the maximum, the two spots can be well resolved. But actually, obviously, this depends on the resist. When the resist is very good, even though the two spots is closer, one here, maybe one here, it can be resolved. If the resist is very good. If the resist is very bad, even something like this, it may not be resolved. So you can see, so the Rayleigh criteria is only a very rough criteria without considering the property of the photoresist. So we will look at the property of the photoresist next time. Thank you.